if you felt like 2025 was a year where every conversation, every headline, and maybe even your insurance premium was just dominated by extreme weather, you weren't wrong.
Not at all.
It felt like weather wasn't just something we predicted anymore. It was, I don't know, it was this persistent, unavoidable reality that was just reshaping everything.
I think that's a perfect way to put it. It was a year that really forced a shift in perspective. And what's crucial for us to get our heads around right away is that despite natural processes that should have acted as a kind of brake on global heat.
Right, these natural cooling cycles.
Exactly, cycles we've historically relied upon. Despite those, global heat records still remained wildly persistently above the baseline we've known.
So we're looking back at a year of, well, undeniable severity.
Undeniable severity, but also, and this is critical, a year of these unprecedented technological leaps in how we actually track these relentless extremes.
Welcome to Meteorology Matters, the podcast that dives deep into the science, chaos, and stories behind the weather that shapes our world. This show was created by meteorologist Rob Jones.
Now, let's get into today's episode of Meteorology Matters.
So let's start this deep exploration by looking back at the sheer scale of what happened globally in 2025. It's the universal question at the end of every year, isn't it? Was it a bad year for extreme weather?
It is, and based on all the research, all the analysis we've seen, the answer is, tragically, an unequivocal yes again.
That yes feels almost too simple.
Oh, it's deceptive in its simplicity because it needs so much context. When researchers finally tallied the numbers, 2025 was, believe it or not, globally, slightly cooler than the record-shattering year of 2024.
Okay, so a tiny dip.
Tiny dip? But here's the critical point, the one that tells you everything about the state of our climate. Despite that dip, 2025 was still far, far hotter than almost any other year on record before 2023.
Wow.
That fact alone just confirms we are operating from a dramatically new baseline.
That slight cooling feels like a, well, meteorological contradiction. If the Earth takes a tiny step back on temperature, why didn't that give us more widespread relief?
Because we're dealing with this massive underlying human-driven force that is just overwhelming natural variability. The really surprising detail, meteorologically speaking, is that this persistent extreme heat happened even while the Pacific was experiencing weak La Niña conditions.
Okay, so let's just quickly clarify La Niña for everyone listening. It's the opposite of El Niño.
Right. El Niño is this recurring natural thing, a phenomenon characterized by unusually cool sea surface temperatures across the central and eastern equatorial Pacific.
And that has a big impact.
A huge atmospheric impact. Historically, that cooling effect tends to pull the average global temperature down slightly for that year. It's one of nature's biggest breaks on global heating.
So the fact that 2025 was still historically incredibly hot, even with La Niña trying to hit the brakes, that means the human-driven warming signal is now so strong, it could just neutralize one of nature's biggest cooling systems.
Exactly. The sheer strength of anthropogenic warming, that's the warming caused by human activity, is just laid bare by this paradox. It means the heat that drove all those destructive extremes across every continent wasn't just some random spike.
It was the new normal.
It was the climate system operating at a dramatically elevated level. This isn't some distant theoretical threat anymore. It is our present, undeniable reality.
And the scale of the impact really supports that conclusion. I mean, researchers didn't just look at temperature anomalies. They analyzed 22 of the most significant extreme weather events globally.
A terrible mosaic, really.
It really was. Catastrophic heat waves, intense floods, devastating storms, persistent droughts, and these uncontrollable wildfires that just claimed countless lives, destroyed infrastructure, and crippled communities.
And every story embedded in those events is tied directly to something that sounds clinically small. It's called incremental warming.
Right.
We're talking about that slow, steady upward creep of global average temperatures, fractions of a degree, that have these disproportionately massive real-world impacts.
To put that in perspective for everyone, we often talk about the 2015 Paris Agreement as this kind of benchmark moment. So how much warming have we actually seen just in the decade since that agreement was signed?
Since 2015, global warming has increased by 0.3 degrees Celsius.
0.3. Just sounds so tiny.
It sounds tiny. It sounds scientifically insignificant. But that fraction represents a massive escalation of risk that has fundamentally changed the odds of extreme weather.
That number, 0.3 degrees C, is so abstract to most people. What does that tiny incremental warming actually mean in terms of daily life, for you and me just walking outside?
It's the difference between a harsh summer and a catastrophic one. That seemingly small rise has already resulted in extreme heat becoming significantly more frequent across the entire globe, adding, on average, 11 extra hot days per year.
11 extra days.
Think about that. That's nearly 2 full weeks of additional, potentially dangerous, life-threatening heat every single year for the whole planet.
11 extra hot days on average. That statistic doesn't just sound chilling it. I mean, it means a fundamental restructuring of what a normal year even looks like.
It does, and it means the type of heat is changing too. It's not just the dry, high temperature heat we worry about. It's the increasingly frequent wet bulb heat events.
Right, where the humidity is the real killer.
That's the one. Wet bulb temperature measures heat and humidity combined, and when it rises past a certain point, the human body literally cannot cool itself by sweating. An increase of 0.3 degrees C pushes regions, especially near the equator, closer and closer to those critical, lethal wet bulb thresholds.
So those 11 extra days are just much more dangerous than they would have been in the past.
Far more dangerous, and the effects just ripple out from there. Agriculture is strained because crops have specific temperature tolerances. You see mass crop failures, reduced yield.
And our infrastructure.
Our infrastructure, which was designed for a climate that doesn't exist anymore, it just starts to buckle. You have asphalt roads melting, rail lines warping, electricity grids struggling because the demand for cooling spikes exponentially with just a few extra degrees.
So the warming makes heat waves longer, and they happen more often, so there's no time to recover.
Exactly. Nature can't recover. Human systems can't recover. There's no break.
And the change in probability for specific local events is even more alarming than that global average.
Oh, absolutely.
Okay.
For specific, well-documented heat waves we've seen in previous years, like that extreme heat that devastated parts of the Amazon, or the severe events that hit West African nations like Burkina Faso and Mali.
Yeah.
Researchers found that the probability of those specific high-intensity events happening again has increased almost 10 times since 2015.
10 times more likely.
10 times. Every single fraction of a degree matters because it shifts the odds exponentially toward disaster. It makes events that were once rare anomalies, once-in-a-century events, now disturbingly routine.
That analysis just drives home the urgency for both mitigation and adaptation. We're getting very close to the limits of what society can actually absorb.
And when we talk about who absorbs that cost, we have to look beyond the generalized impact. Extreme weather does not distribute its effects equally.
No.
It consistently and devastatingly hits those who are already marginalized and vulnerable the hardest.
We saw some particularly detailed research that illustrated this profound inequity across regions of the global south in 2025.
Yes, there was a study focused on South Sudan which provided a powerful, really granular example of how these climate hazards intersect with pre-existing social structures.
What did they find?
They found that women in South Sudan are disproportionately affected by extreme heat, mainly because of their concentration in informal heat-exposed work.
Can you paint a clearer picture of what that informal work actually looks like on the ground?
We're talking about essential economic activity that often provides zero shelter. Things like subsistence agriculture, spending hours tending fields under intense sun, or jobs like street vending, where the only place to do business is directly exposed to peak daytime heat.
And these are jobs that are critical for family income.
Absolutely critical, but they offer zero mitigation against severe heat.
So it's not just the exposure to the heat itself, and during a heat wave, that work gets even harder.
It intensifies. Family members are more likely to fall ill, so their own exposure to dangerous conditions increases while their mobility and ability to earn a living shrinks. And the impact spills into the next generation. Extreme heat forces widespread school closures, which immediately interrupts the education of girls more severely than boys.
Reinforcing existing gender inequalities and just perpetuating the cycle of vulnerability.
Exactly.
What's equally important, and something the analysis really pointed out, is that this inequity extends right into the scientific process itself. It's not just that the impact is unequal, it's the evidence we have to study those impacts. It creates a kind of scientific blind spot.
That is a critical finding. Many studies that focused on severe weather in the global south in 2025, specifically heavy rainfall, they ran into the same problem over and over again.
Which one?
Significant gaps in localized, on-the-ground observational data. And even worse, the studies had to rely heavily on global climate models that were fundamentally developed, calibrated, and optimized, primarily for the conditions and infrastructure of the global north.
So we're trying to understand the hyperlocal effects of massive rainfall in a place like South Sudan, using models that were optimized for, what, Kansas or Germany?
In effect, yes. The scientific foundation is uneven. When you lack that granular, reliable local data, and your predictive tools are biased toward different atmospheric conditions and terrains, it severely hinders your ability to draw confident, actionable conclusions.
And that cripples local planning where it's needed most.
It absolutely cripples it, in the regions already experiencing the most immediate and severe consequences. Addressing this is just as vital as reducing emissions. We need investment in closing these scientific data gaps globally so marginalized communities can build genuinely effective, data-driven resilience.
That sets a very intense, very sobering stage for 2025. The overall warming picture is relentless, and the human cost is so unequally distributed.
So let's pivot now from that persistent global heat to a specific, terrifying example of catastrophic weather. The Atlantic hurricane season. This was a year where the early forecast predicting a highly active season, well, they proved devastatingly accurate.
The season was undeniably busy. Overall, we saw 13 named storms, which is a busy count. And frighteningly, 3 of those intensified into Category 5 hurricanes.
3 Cat 5s.
3. This puts 2025 among the most intense seasons on record, just based on that peak strength.
There was one small silver lining, for the U.S. coastline at least. For the first time in a decade, a hurricane did not make landfall on American soil.
That localized good fortune, unfortunately, did not extend to our neighbors in the Caribbean. We have to zero in on the most destructive storm of the year, Hurricane Melissa.
A truly devastating storm.
Yeah.
It was a monster, a Category 5 that achieved maximum intensity, slamming Jamaica in late October with sustained winds of 185 miles per hour. It devastated communities and, tragically, resulted in dozens of deaths.
Hurricane Melissa, in its sheer intensity, it really highlighted a painful lesson that ties right back to our discussion on adaptation in this rapidly warming world.
It showed the clear limits of preparedness. We talk constantly about the need for adaptation, building better seawalls, improving warning systems, enforcing building codes, and those are all absolutely essential for preventing massive loss of life from less intense storms.
But Melissa was different.
Melissa made it painfully clear. When a storm of that maximum intensity strikes a small island nation like Jamaica, even relatively high levels of preparedness simply cannot prevent catastrophic losses and infrastructure annihilation. The physical force is just too great.
Which emphasizes that forecasting alone isn't the solution, but it is that critical first step. And this is where the story gets really compelling, shifting from the tragedy of the storm to the technological leaps happening in the background.
Yes. A week before Melissa made landfall, forecasters were in agony. The traditional forecast models were just disagreeing widely on the storm's eventual track.
Right.
One model had it moving north toward the Bahamas, another had it tracking directly into the Gulf of Mexico. This uncertainty, that common, agonizing cone of uncertainty, is a huge challenge when you're issuing life-saving warnings.
The pressure on the human forecasters must have been just immense, trying to synthesize all those competing possibilities.
It was. But amidst all that confusion, one specific model delivered an outlier forecast that proved to be exactly right.
One all about it.
It predicted both Melissa's precise track into Jamaica and, crucially, it forecast its Category 5 intensity. That model was Google's DeepMind AI-based hurricane model.
A perfect call in a chaotic life-or-death situation. That kind of endorsement for an AI model must have been impossible for the meteorological community to ignore.
It was a watershed moment. Former officials from the National Hurricane Center later analyzed the 2025 performance of all the available guidance. They went on record to call the Google DeepMind model the best guidance we saw this year.
Wow.
They noted its stunning accuracy, especially when you compare it directly to the results from the long-standing traditional physics-based systems.
That endorsement suggests AI isn't just a useful addition anymore. It might be fundamentally changing how meteorology even works.
Yeah.
Let's really unpack the core difference for the listener, because these models operate on entirely separate philosophies, don't they?
They really do. You can think of it in terms of philosophy. Traditional weather models like the Standard Global Forecast System, the GFS developed by the National Oceanic and Atmospheric Administration, or NOAA.
Right.
They rely on these complex first-principle equations. These models are like the atmosphere as a physics textbook. They calculate how wind, moisture, and heat move and interact using established scientific laws. They're trying to predict the future based on pure, continuous mathematical calculation.
So if a traditional physics-based model is solving this massive complex equation, how does an AI model, like Google DeepMind, approach the same problem?
It approaches it like a detective studying a crime scene archive. AI models don't necessarily know physics in that traditional sense.
Okay.
Instead, they focus intensely on historical patterns. They're trained on decades, even centuries of past weather data, looking for subtle, nonlinear relationships that a human or even a pure physics model might miss. They just ask, based on thousands of similar atmospheric setups in history, what was the most probable outcome?
That pattern-based approach explains why AI has, for a while now, been pretty good at track forecasting. That's essentially a large-scale pattern recognition problem.
Exactly. Storm tracks are governed by these massive, predictable atmospheric steering currents. That's why AI could always see the path well. But historically, AI models always struggled with intensity.
And why is intensity, how strong a storm will be, so much harder to predict than where it's going?
Because intensity is governed by these small, chaotic, localized processes. Things like eyewall replacement cycles, internal storm dynamics, specific wind shear values.
Things happening on a much smaller scale.
Right, and they're notoriously difficult to capture in generalized data. But the Google DeepMind model overcame this. It incorporated highly specific historical data detailing precisely how past hurricanes developed and intensified under all these various conditions, and that allowed it to forecast maximum intensity with the accuracy we saw with Melissa.
This shift, though, while it's delivering better forecasts, it introduces a new and kind of challenging dynamic for experienced human forecasters. It's this critique called the black box problem.
It's a genuine operational concern. When a forecaster uses a physics-based model, they can look at the data outputs, the pressure gradients, the wind shear fields, and they can trace the precise physical mechanism that led to the prediction. They know why the storm is being steered northwest.
But the AI model doesn't offer that same transparency.
Not always. Because the AI models focus on these subtle, learned historical correlations, the process can feel opaque, a black box. Massive amounts of data go in, a highly accurate forecast comes out, but the specific, understandable mechanism it used to connect the input to the output might be invisible to the human.
But if the forecasters don't know why the AI made a choice, let's say the AI forecasts a radical path that their trusted GFS physics model completely disagrees with, how can they trust the AI enough to override the physics?
Yeah.
Isn't that a massive, potentially catastrophic liability when human lives are at stake?
That is the essential challenge of integrating AI. It requires a massive leap of faith in the underlying statistical accuracy of the AI, even without the comfort of that physical traceability.
All right.
And forecasters are inherently skeptical, and they should be because they have to be accountable for their warnings. The only way you build that trust is through repeated, proven performance, like the perfect call on Hurricane Melissa.
It sounds like the human element, the essential judgment of the experienced meteorologist, is actually becoming even more critical, not less. Now they have to decide which computer outlier to trust.
Absolutely. The consensus is clear. AI will not replace the long-standing physics-based models or the essential judgment of experienced forecasters, but it's clearly going to be a key foundational component that provides an alternative perspective and critical time savings.
It's not a replacement. It's a powerful new tool in the toolbox.
Exactly.
And the practical benefit for you, the listener, is really simple. As our coastlines become more populated and as these storms become more intense, we desperately need more time. More time to get people out of the way, to secure property, to activate infrastructure. Forecasts further and further into the future become vital, and AI is delivering that crucial time advantage.
And this innovation moved beyond the experimental phase really fast. We're now transitioning from that successful proof of concept stage, like Google DeepMind's stellar performance, to large-scale operational use deployed by major government agencies.
Right, like the National Oceanic and Atmospheric Administration, or NOAA.
NOAA has now deployed a groundbreaking new suite of operational AI-driven global weather prediction models as of December 2025.
This feels like a profound strategic leap forward for American weather model innovation. It's a signal that the U.S. weather infrastructure is fully committing to the AI revolution.
It really is. The mission statement from NOAA was clear and multifaceted. They're aiming to provide improved accuracy for large-scale weather and tropical tracks, and to deliver that guidance much faster and at a dramatically lower cost than the current traditional models allow.
The cost and speed element is the often overlooked secret weapon of AI modeling, isn't it? What is the most transformative feature of these new NOAA AI models compared to the GFS running on those massive supercomputers?
It is, without question, computational efficiency. We cannot overstate this. These AI models use a tiny fraction of the computational resources of their traditional physics-based counterparts. This isn't just about saving money. It's a game changer because it allows NOAA to run models more often at higher resolution and to run many more members in their ensemble systems. It basically democratizes access to high-quality modeling.
Let's look at the specific models that NOAA has rolled out. We can start with the Artificial Intelligence Global Forecast System, or AIGFS. This is the single deterministic forecast model.
Right, so the AIGFS is designed to generate a single forecast that's comparable in quality to the traditional physics-based GFS. And on the performance side, NOAA found an immediate gain: improved forecast skill for many large-scale atmospheric features, and a significant measurable reduction in tropical cyclone track errors, especially at longer lead times.
So just like DeepMind, the AI is delivering superior guidance on where the storm will go.
That's right.
Now let's talk about the efficiency, because these numbers are just astonishing.
They redefine what's possible. A single 16-day forecast from the AIGFS uses only 0.3% of the computing resources required for the traditional GFS.
0.3%. Less than half of 1% of the power.
It's incredible. And the time savings are just as vital. It finishes in approximately 40 minutes.
40 minutes, compared to a traditional GFS run that can take hours and hours.
Exactly. That dramatically reduced latency means forecasters get critical data much, much faster. Speed means earlier warnings, and earlier warnings mean lives saved.
That speed advantage is huge. But we did note there was one initial area for improvement in this first version, v1.0.
Yes. The initial testing confirmed that prevailing challenge in AI. Version 1.0 did show a slight degradation in tropical cyclone intensity forecasts compared to the traditional physics-based model.
Still the hardest nut to crack.
It is, but the speed gains and the track improvements were so significant that they deployed it operationally immediately, with the understanding that future versions will focus heavily on boosting that intensity accuracy.
Okay, next up is the really essential component of modern forecasting: the ensemble system. NOAA deployed the AIGFS, the Artificial Intelligence Global Ensemble Forecast System. Before we get into the AI version, just remind us, what is the core role of an ensemble system?
An ensemble system is maybe the most crucial tool forecasters have for managing uncertainty. Instead of running the model just once, you run it many times. In NOAA's case, 31 times. And each run starts with slightly different initial atmospheric conditions.
So you get a range of possibilities.
You get a fan of possibilities, a range of probable outcomes, rather than one single confident solution. It helps meteorologists and decision makers understand the overall forecast uncertainty and figure out the highest risk scenarios.
And how did the AI-based AGFS perform against the traditional Global Ensemble Forecast System, the GEFS?
The AI version's forecast skill is comparable to the traditional ensemble system, so the quality is maintained, but it provides a huge benefit. It extends reliable forecast skill by an additional 18 to 24 hours.
A full day.
An enormous gain in lead time. And again, the efficiency is astounding. It requires only 9% of the computing resources of the traditional GEFS.
Those savings and time gains are phenomenal. But the real innovation breakthrough, the thing that makes NOAA's deployment a global first, is the HGEFS, the hybrid GEFS. This sounds like the ultimate answer to that black box problem we were talking about.
This is where the physics and the patterns marry. It acknowledges that neither system is perfect on its own. The HGEFS is a pioneering 62-member grand ensemble.
Okay, what does that mean?
It's created by combining the 31 members of the physical GEFS ensemble with the 31 members of the AI-based AIGF.
So the hybrid model is essentially letting the physics tell us the rules of the atmosphere, while the AI uses the patterns of history to refine those rules, all in one gigantic, robust package.
That's a perfect way to describe it. By combining two fundamentally different modeling systems, one based purely on physical equations, one based on learned historical patterns, the HGEFS creates an ensemble that's twice the size, making it much more robust. And crucially, because the two systems fail for different reasons, combining them more effectively represents the full spectrum of forecast uncertainty.
And the result of that blending, did it actually work to create better forecasts?
It consistently worked. The HGEFS consistently outperforms both the AI-only system and the physics-only system across most major verification metrics. It is a first-of-its-kind operational approach globally, and it confirms that the future of forecasting is hybrid.
It's physics informed by history.
All run with maximum computational efficiency.
And this entire suite, the AIGFS, AGSS and HGEFS, this wasn't just whipped up overnight. This is the culmination of a huge collaborative effort.
A massive undertaking. It resulted from something called Project EGL, which was a collaborative initiative involving various elements of NOAA, the National Weather Service, its Oceanic and Atmospheric Research Labs, the Environmental Modeling Center, and the Earth Prediction Innovation Center.
So they leveraged work from the private sector, too.
They leveraged foundational academic and private industry work, specifically Google DeepMind's breakthrough GraphCast model, and then they fine-tuned it using NOAA's own massive global data assimilation system data.
So they took the best of theoretical private industry innovation and married it with the essential operational necessities and the vast real-time data flow of the National Oceanic and Atmospheric Administration. That is how you achieve a quantum leap in forecasting capability.
The administrator of NOAA summed it up perfectly. This is a new paradigm for providing improved accuracy, faster delivery of forecast products, and at a dramatically lower operational cost. The pace of innovation is finally accelerating to meet the pace of climate change.
As we wrap up this deep dive into 2025, let's work it all back together into a single narrative. From the persistent, overwhelming heat, despite the natural cooling efforts of La Niña, which showed us the relentless nature of human-driven warming, to the profound social inequities highlighted in regions like South Sudan, 2025 really showed us the current, harsh reality of a planet that is fundamentally warmer and more volatile.
And the devastating power of Hurricane Melissa in the Gulf of Mexico region was the perfect, terrifying case study of that. It reminded us that the ultimate devastation is still possible, and that even the best preparation has its limits when a storm achieves that kind of maximum intensity.
But the rapid pace of innovation, evidenced by both the success of Google DeepMind and the operational deployment of NOAA's hybrid AI models, it suggests that while the weather is becoming undeniably more extreme, our ability to see it coming, and faster, is reaching astonishing new heights.
It really is. It's offering that extra vital 18 to 24 hours of warning time. It's a race against the clock. As the climate changes and volatility increases, our tools for prediction have to evolve even faster just to keep pace.
I want to leave you with this final provocative thought. While forecast accuracy is dramatically improving and we celebrate every single hour of extra lead time, Hurricane Melissa reminded us that adaptation, no matter how good, has hard limits. Knowing a Category 5 is coming earlier is absolutely vital for saving lives, but what truly prevents catastrophe? Is it only forecasting? Or is it fundamentally reducing the fuel for these storms, addressing the root cause of the warming that makes them so powerful in the first place? That's the question we have to grapple with moving forward. If you want to keep exploring the science, chaos, and stories behind the weather, please like, follow, comment, and rate the Meteorology Matters podcast.
You can also follow meteorologist Rob Jones on Instagram at Meteorologist, on TikTok at TV Meteorologist, and on YouTube by searching for Rob Jones Hurricane, where you can also find the Meteorology Matters podcast playlist.
You've been listening to Meteorology Matters, created by meteorologist Rob Jones.
Thanks for listening, and remember, meteorology always matters.